Hi, today we're going to solve the following linear Diophantine equations. 12x plus 9y equals 15, and 8x plus 10y equals 17. But first, what are linear Diophantine equations? Simply, they're equations where we are looking for integral solutions only. They are named after 3rd century Greek mathematician Diophantus, who worked with such equations and was only interested in integer solutions. So no fractions, no decimals, and definitely no square roots. Let's go back to our first equation. 12x plus 9y equals 15. If we look at these numbers, we can see that 12 is divisible by 3 and 4. 9 is divisible by 3 and itself. And 15 is divisible by 3 and 5. This means that we can divide all parts of the equation by 3 to make it a little more friendly. So 12 divided by 3 is going to give us 4x plus 9 divided by 3 gives us 3y equals 15 divided by 3, which is 5. We end up with 4x plus 3y equals 5. Now we can use the Euclidean algorithm to find the greatest common divisor, or GCD, of the coefficients of x and y. So the GCD of 4 and 3 can be found by setting 4 equal to some number times 3 plus a remainder. So 3 only goes into 4 once as 3, which means that 4 minus 3 gives us a remainder of 1. Now our goal is to get a remainder of 0, so we're going to keep going. Now 3 is going to move over here, and it's going to equal something times our remainder, gives us a new remainder. And that something is going to be 3, because 1 goes into 3 times, and we're left with a remainder of 0, which is what we wanted. So now we know that the GCD of 4 and 3 is 1. Let's call this D. Now, according to Bezout's identity, if the GCD divides this number, 5, then we get solutions. And because 1 does go into 5, we know that there are solutions to this Diophantine equation. Let's find them. To do so, we go back to the Euclidean algorithm. Now, since in this equation we got 0, we're going to go back up to this equation here, and we're going to rewrite it in terms of the remainder. So, 4, we want to isolate the remainder. So we're going to move this to the left side by subtracting it. Now we're going to rewrite this a little bit using some arithmetic by saying that 4 plus -1 times 3 is equal to 1. And I want it to look even more like our original equation, so let's move some numbers. We know that 4 is going to be times something, and in this case it's just 1, plus 3 times the negative 1 is equal to 1. Now this is not quite our solution because we have a 1 here, but we need a 5. So we're going to multiply this entire equation by 5. We're going to get 4 times 1 times 5 plus 3 times negative 1 times 5 equals 1 times 5, which is 5. That's going to give us 4 times 5 plus 3 times negative 5 equals 5. And there we have a particular solution to our linear Diophantine equation, where this 5 we'll call x0, and this negative 5 we'll call y0. Writing it as an ordered pair, x0, y0 equals 5, negative 5, which is our particular solution. But we're not done yet because we want to find the general solution to the linear Diophantine equation 4x plus 3y equals 5. To find this general solution, we are going to use the following two formulas. For x, we're going to use our x value in the particular solution, which is x0, plus b over d times t. And for y, we're going to use our particular solution for y, which was y0, minus a over d times t. And here, t is going to be an integer. So let's plug in our numbers. X equals 5 plus our b, which was 3. So these are a, b, and we know that d, which was our GCD, was 1. So 5 plus b over GCD 1 times an integer is going to give us our solution, but we can clean that up some to say that x equals 5 plus 3t. And y is going to be negative 5 minus a, which was 4, over GCD 1t, which cleans up to negative 5 minus 4t. And here we can use this to write our general solution. So our general solution can be written as an ordered pair where x is 5 plus 3t, comma, y, which is negative 5 minus 4t, where t is an integer. And there we have our solution. Now let's look at 8x plus 10y equals 17. So 8 we know to be divisible by 2 and 4. 10 is divisible by 2 and 5. But 17 is prime, which means it's only divisible by 1 and itself, which means that we cannot reduce this equation any further. So let's go to our Euclidean algorithm to find the greatest common divisor for these coefficients. So the GCD of 10 and 8, and we're going to set 10 equal to some number times 8 plus a remainder. 8 goes into 10 just one time. would have a remainder of 2. And we'll continue since our remainder is not 0. So now we set 8 equal to some number times 2 plus a remainder. 2 goes into 8 4 times, and that gives us a remainder of 0. Which means that our GCD of 10 and 8 is 2. Now we go to Bezout's identity, which says that 2, if 2 divides 17, then we have solutions. However, since 17 is prime, then 2 cannot divide 17, and therefore we have no solutions. So we can say that 8x plus 10y equals 17, the linear Diophantine equation, has no integer solutions. Thanks for watching.